Hello everyone, I'm Shangu from University of California, Irvine. Today I'm so glad to be here for presenting my research which entitled An Evaluation of Air Quality Impacts from Different Urban Greening Strategies in Los Angeles County. Well, both anthropogenic and biogenic volatile organic compound emissions have essential effects on urban air quality, especially for megacities like Los Angeles. As shown in the left figure in this page, biogenic VOC emissions like isoprene and monoterpenes are typical secondary organic aerosol precursor, which could quickly react with NOx and other VOCs emitted from anthropogenic sources to form ozone and particle matter. These secondary products, including like ozone and particle matter, are harmful to humans' health and affect regional climates. Even though AVOC and BVOC plays important roles in urban air quality, the trend of AVOC and BVOC are quite different in megacities. For anthropogenic VOC, it keeps decreasing due to the air pollution control implemented by Air Resources Board, whereas BVOC emissions may increase because of more planted trees by urban greening strategy. Therefore, an interesting question comes out. What's the potential change of urban air quality in Los Angeles under this opposite trend for AVOC and BVOC? Then let's take a look at the major challenges for urban air quality management. As summarized below, there are three major challenges for urban air quality. The first one is land use and land cover change. The second challenge is the effect from future climate change. The last one, urban greening strategy. You may be confused about this challenge. How could this strategy affect urban air quality? Well, yes, it does, because the planted trees may enhance biogenic VOC emissions if these trees have high BVOC emissions potential. Well, the figure shown in this page is adopted from Mars paper published in ACP, who illustrates the large effect of urban landscape on biogenic emissions and the subsequent ozone formation. The types of trees may be cautiously selected to take into account of the biogenic VOC emissions and during the afforestation of cities. Therefore, the goal of this project is to investigate how would the different types of future urban greening strategies, say isoprene emitters versus monoterpene emitters, will change the secondary pollutant production in Los Angeles County. The method we used are shown in here as the detailed flowchart. Well, for the part of anthropogenic VOC speciation and formation potential calculation, firstly, 2014 National Emissions Inventory was selected as anthropogenic VOC emissions data. Well, during this process, 8 major sectors were considered in this study, like fires, mobile, fuel combustion, industrial, solvent sources, well, etc. And these major sectors were divided into 47 subsectors. And secondly, we use species database and smoke processing system to calculate the emission amount of individual VOC. For the part of biogenic VOC emissions, we utilize update local emission factors of trees over Los Angeles County to drive the Pocket Mega3 model for producing biogenic VOC emissions inventory in Los Angeles County. After calculating both speciated anthropogenic and biogenic VOC emissions, then the ozone formation potential, what we call OFP, and secondary organic aerosol formation potential, what we call SOAP, for each VOC were calculated based on the parameters provided by previous studies. Here shows the formulation in calculation OFP and SOAP for each VOC species under different emission sector. For example, for OFP calculation, we apply for MIR, the maximum incremental reactivity, which represents the potential of one VOC species to form ozone under optimum reaction conditions. After finishing the base case analysis, which I introduced above, we designed several potential future scenarios to investigate the effect of different urban greening strategies that would plant isoprene emitters versus monoterpene or sesquiterpene emitters on secondary pollutant formation potential by comparing the relative changes of OFP and SOAP between AVOC and BVOC. As we shown in here, the base case represents the initial AVOC and BVOC emissions in Los Angeles County for 2014 year. Then for future scenarios in the year of 2050, we conducted as follows. The scenario 2 is considered with reduced AVOC emissions and the same BVOC emissions as the base case, while in the scenario 3, again, reduce AVOC emissions, but BVOC emissions increase with the same emission type as the base case. For the scenario 4, which is the same as the scenario 3, considers all additional plants are isoprene emitters. For the scenario 5, which is the same as the scenario 4, while all plants are considered as monoterpenes or sesquiterpenes emitters. And due to the time limitation here, more detailed information will be shown in the future published paper. And here's the results for speciated anthropogenic VOC emissions and their OFP and SOAP in the base case. As shown in this table, the alkanes have the largest emission with a contribution of 71%, followed by oxygenated VOCs and aromatics. But OFP and SOAP show a different order rank. For the OFP, the alkenes have highest contribution, which is 35%, followed by aromatics and alkanes. For the SOAP, the aromatics make greatest contribution with almost 50%, followed by the alkanes. And the following figure illustrates the source contributions of 10 individual species with the largest OFP and SOAP contributions. In the left figure, the ethylene, the most photochemically active species for ozone formation, mainly originated from mobile and miscellaneous sources. The amphixylene are primarily emitted from mobile and solvent source. For the SOAP, the mineral spirits are almost all coming from the solvent source, and the benzene were abundant in mobile and industrial source. Overall, the mobile and the solvent use are the two sectors that most significantly contributed to the majority of the top 10 species in both OFP and SOAP. In the next, the results of biogenic VOC emissions and their OFP SOAP are shown in this table. We could see that isoprene is the largest contributor to both emissions and OFP, and then monoterpenes also have significant contribution to OFP. In contrast, the SOAP, while the biogenic VOC shows a different pattern. The sesquiterpenes is constituting the highest fraction of total SOAP, with about 50%, and the following are monoterpenes and oxygenated monoterpenes. To illustrate the potential impacts of different tree planting strategies, we analyze the projected AVOC and BVOC emissions in future 2050 year compared with the base case. As shown in this table, we could see that the total BVOC emissions almost double in all future scenarios, and peak in the monoterpene and sesquiterpene case. In all cases, isoprene still dominates BVOC emissions in most future scenarios, and monoterpene emissions will be comparable with isoprene emissions in high monoterpenes and sesquiterpene emitter case. This phenomenon indicates that biogenic VOC emissions will significantly increase in future years if the trees planted over Los Angeles by urban greening strategy have high BVOC emissions potentials. As for the changes of OFP and SOAP, it is obvious even though BVOC emissions increase significantly, it still only accounts for a small fraction of total VOC emissions due to the dominant role of AVOC emissions in the total VOC. In addition, for OFP and SOAP, the increase of BVOC emissions doesn't have obvious effects on SOAP and OFP in all scenarios, which is attributed to their low emission fraction. Given this situation, we could conclude that in Los Angeles County, the implementation of urban greening programs will aggravate urban air quality, since the contribution from the increase of BVOC emissions to OFP and SOAP are pretty small compared with AVOC emissions contributions. And what's more, the opposite trend of AVOC and BVOC in LA County is still beneficial for air pollution mitigation, and keeping the decreased trend of AVOC should be considered as the main strategy for reducing ozone and SOA formation. However, additional work is needed to consider the change of meteorological conditions in the future scenarios due to the effects of climate change. Well, finally, we thank Professor Alice Genfer for his kind help in this project and acknowledge that this work is funded by the University of California, Irvine. And thank you for all listening, and now welcome for the questions. And if you would like to discuss any contents of my slides with me, please feel free to reach out through my email addresses listed in here.